Good morning, girls. Previous class we done the integrated rate equation for a zero order reaction. Integrated rate equation for a zero order reaction, and this is very important. It is 3-mark question. Okay, they will ask integrated rate equation for zero order or integrated rate equation for first order reaction. So today is the integrated rate equation for first order reaction. So derivation for the integrated rate equation for a first order reaction. Okay. So we know, now consider a reaction. R gives P. R means what? Reactant gives product. So it is a first order reaction. So rate is proportional to the first power of the reactant. Okay. So rate is proportional to the first constant power of the concentration of the reactant. In zero order reaction, the rate is directly proportional to the zero power of which one? The concentration of the reactant. Here rate is proportional to what is the first power of the concentration of reactant. So we can write rate equal to K into concentration of R raised to 1. Okay. Here K is known as what? Rate constant or velocity constant. Okay. But we know the instantaneous rate is equal to minus d into concentration of R divided by dt. Okay. So normal rate equal to K into concentration of R raised to 1 according to rate law expression. Rate equal to minus d into concentration of R divided by dt. So equating these two equations, because this left side is equal, so right side we can equate. We will get minus dr by dt equal to K into concentration of R. I am not writing 1 here because something raised to 1 equal to that only. So I am not writing. So minus d concentration of R divided by dt equal to K into concentration of R. Same as zero order only. Okay. So just we are rearranging this equation. Minus dr by this one. Minus we can take this side. Okay. So d into concentration of R divided by R equal to minus K dt. Just rearranged. Just we are taking the R terms in concentration of R terms in one side and other in next side. So d into concentration of R divided by R equal to minus K into dt. Okay. Then integrating this equation. So on integration, integral of, just I am splitting and writing, this is dr by R as 1 by concentration of R into dr. To integrate, to easily we can integrate that, equal to minus K into integral dt. Here K is a constant, no need of integrating. Okay. So we know the integral of 1 by x dx equal to what? ln x. All of you know that. Okay. So integral of 1 by x dx equal to ln x. So this is us in this form, no? So integral of 1 by concentration of R into dr equal to what then? ln r. Right? Because integral of 1 by x dx equal to ln x. So this is in the same form. So integral of 1 by r dr equal to ln r. That is equal to integral constant we are not integrating into integral of dt equal to what? T plus I. What is I? I is the integration constant. Here integral of 1 by concentration of R into dr is in the form of integral of 1 by x into dx, that is equal to ln x. So this side we can write it as ln r. That is equal to minus K integral of dt equal to T plus I, where I equal to what? Integration constant. So next what we have to do? We have to find out the integration constant. So finding out the integration constant, when t equal to 0, which equation? This is equation 1. When t equal to 0, then concentration of R equal to which one? Concentration of R0. We are considering when t equal to 0 in the beginning. Okay, it is not started in reaction. So when t equal to 0, the concentration of R will be R0. So we have to substitute that values in equation 1. So we will get ln R. R will be become R0. So ln R0 equal to minus K into T equal to what? 0 plus I. Okay. So we will get what? ln R0 equal to. So this part will become 0, right? So we will get which one? This one, I equal to ln R0, because this is become 0. So I equal to ln R0. So we got the value of which one? I equal to integration constant I equal to ln R0. So we have to substitute the value of I in which one? This first equation. Okay. So how we will write is, so substitute the value of I in which equation? Equation first. Okay. So we will get ln concentration of R equal to this one minus Kt plus which one? I equal to what? ln R0. I equal to ln R0. Clear? We got I value, integration constant. We have to substitute this value in which one? The equation first. So we got this one. This is known as which one? Equation 3. This is equation 3. So ln concentration of R equal to minus Kt plus ln R0. Clear? Then just rearranging this equation, we will get Kt equal to, just I am taking left side, Kt equal to ln concentration of R0 minus, this is R0, ln concentration of R. Just rearranging the equation, okay. Taking Kt left side, so minus sign will go. So Kt equal to ln concentration of R0 minus ln R0, concentration of R. Okay. So we know that ln R0 minus, in ln minus, in ln the minus means what? That is division. Okay. Right. Product means what is that? It is addition. Okay. So here it is minus. So we can write this one as which one? Kt equal to ln R0 divided by ln concentration of R. Getting what I am telling? This is in logarithm. The division, what is that? Subtraction means we can, it is division. Addition means it is what? It is multiplication. Okay. So here it is subtraction. So we can write ln concentration of R0 divided by ln common we can write. No need of writing separate. Okay. So ln concentration of R0 divided by concentration of R. Okay. So K equal to, how we will write? 1 by T ln concentration of R0 divided by concentration of R. Okay. So this is which one? K equal to 1 by T. Just I took the K here, T here. So K equal to 1 by T ln concentration of R0 divided by R. Okay. Then I am removing which one? The natural logarithm. If you are converting ln to the 10 base logarithm, we have to multiply with which value? 2.303. Which value we have to multiply? With 2.303, and this equation is marked as 4. Okay. So here this equation we can mark as 3. This is marked as which one? 3. Okay. This one is equation 4. So K equal to 2.303 divided by T. We converted ln into what? 10 base logarithm. Log concentration of R0 divided by concentration of R. Okay. So K equal to 2.303 divided by T log concentration of R0 divided by concentration of R. So this is the integrated rate equation for a first order reaction, and this reaction we can consider as equation 5 because other some forms are coming equations. Okay, so that is why. So what is the integrated rate equation for a first order reaction? K equal to 2.303 divided by T log by it is a 10 base logarithm. Okay, concentration of R0 divided by concentration of R. Okay, so this is the integrated rate equation for which one? The first order reaction. Okay, this equation is having some other different forms that I will discuss now after this. Okay, so K equal to 2.303 log R0 divided by R. Clear? Okay, so that is about which one? This derivation. Clear all of you. Next we have to derive different form of this equation. Okay, different form of rate equation for a first order. Okay, so we know this is equation 3 already we wrote, in that equation 3 equal to ln r, concentration of r equal to minus kt plus ln r0, and this is which one? Our equation rate for which one? Integrated rate equation for first order reaction, that is k equal to 2.303 t log r0 divided by r we derived. So equation 3 this one and equation 5. Okay. Then this is the equation 3. We have to write the equation 3 at mainly this one they will ask for problems. Okay. So we have to just arrange the equation at t1. Okay. We have to write the equation 3 at t1 when t equal to t1 at the time t1. The equation 3 can be write as ln r1. t1 means r1 equal to minus k t1 plus ln r0 at time t1. Rearranging the equation 3 at time t1, and at time t2 what will be there? ln concentration of r will become concentration of r2 equal to minus k t1 will become t will become t2 plus ln concentration of r0. Got it? Okay, so we are deriving the one different form of the equation, integrated rate equation, that is mainly used for doing problems. Okay, so we know this is equation 3. Okay, rearrange that equation at time t1 and t2. So time t1 we will get this one, and time t2 we will get this one, and name it as equation 6 and 7. Okay, then equation 6 minus 7, subtracting, that is 6 minus 7, we will get 6 equal to, we know which one? ln r1 minus, left side I am subtracting. Okay, 6 ln r1 minus ln r2 equal to, this is minus kt1 plus ln r0 minus equation 7 minus of minus, here minus kt2 plus ln r0. Clear? Okay, just to left side we are subtracting ln r1 minus ln r2 equal to minus kt1 plus ln r0 minus, subtracting, minus kt2 inside the bracket plus ln r0. Then cutting the common term, left side no cutting. Okay, so we will get ln r1 minus ln r2 equal to, here this one ln plus ln r0, here what is there? Here plus ln r0, but it is minus. Taking the minus inside the bracket, here we will get a minus. So this one and this one will get cancelled. Okay, so equal to minus kt1, here minus into minus plus kt2. Clear? So ln r1 minus ln r2 equal to minus kt1 plus kt2. Just rearranging that equation, we know minus in logarithm, it is minus means it is, we can write it as division. Okay, so ln r1 divided by ln r2 equal to k. Just I am rearranging, taking the k outside. K equal to, can I write k equal to t2 minus t1? Then we will get, what is that? kt2 plus kt2. This is minus kt1. Okay, so k into t2 minus t1. Clear? Then k equal to 1 by t2 minus ln concentration of r1 by r2. Can I write it? Okay, so k equal to, just rearranging, this part will go, this one 1 by t2 minus t1 into ln concentration of r1 divided by r2. So after that what we have to do? We have to convert the ln into natural logarithm into which logarithm? 10 base logarithm. 10 base logarithm means what we will do? We will just multiply with 2.303. So this equation k equal to 2.303 divided by t2 minus t1 into, ln will be converted to 10 base logarithm, log 10 concentration of r1 divided by concentration of r2. So this is the, at a different time, what is t1 and t2, what is the equation for a rate constant in a which one? First order reaction. K equal to 2.303 t2 minus t1 log 10 r1 divided by r2. So you can write one more form, K equal to 2.303 divided by T2 divided by T1. They will give two different times and you have to calculate the rate constant. We will do the problems. Log 10. In place of concentration, we can write it as C1, concentration of the reactant 1, and C2 for the concentration of reactant 2. Not reactant 2, at a time T1, concentration of the reactant, and at time T2, concentration of the reactant as C1 and C2 we can write. So, K equal to 2.303 divided by T2 minus T1 log 10 C1 by C2. Okay, so that is at different two different times. Okay, so that is clear all of you. This is at time T1 and T2. What is the rate constant? So now we derive at different two times T1 and T2 what is the equation for the rate constant. Okay, so one more form is given in the textbook. It is easy from equation 3 again. Just now we got one form that is at different temperature T1 and T2. Here just rearrange the equation 3, one more form is they derived. Okay, so here we know ln concentration of R equal to minus kT plus ln R0, that is which one? Equation 3. Just they rearrange the equation and we will get ln R minus ln R0 equal to minus kT, nothing. This one is here, this one we are taking. So ln positive ln R0 will become, it will be converted to minus ln R0 because we are taking left side, equal to minus kT. Okay, we know here it is minus. Subtraction means what is it? It is division. So ln concentration of R divided by R0 equal to minus kT. Okay, so according to the, we are removing the logarithm. Left side we are removing the logarithm. So right side it will become the exponent term. Okay, it will become the exponent term. Okay, so ln R divided by R0. I removed the ln. So just taking the concentration of R. Okay, then R0 will go this side. This side we removed the ln for R and R0. After that concentration of R we are writing. Concentration of R equal to, because R0 will go to that side, R0 into, I removed left side ln, so this side is in this side, right side it will become the exponent term. So concentration of R equal to R0 into e raised to minus kT. After removing the ln only I took to right side. So concentration of R equal to R0 into e raised to minus kT. So this is the one more form of which one? The rate, one more form of integrated rate equation for a first order reaction. If they are asking derive the integrated rate equation for a first order reaction, means you have to derive this one till this one. After that, if they are asking especially like that at T1 and T2, what is the integrated rate equation, or you derive one more form of the integrated rate equation, then you can derive this one also. Till here is compulsory, that is the first I derived. Okay, so that is clear. So three forms we did derived. Okay, first one this one, then at two different time T1 and T2, then this one, just rearranging the this equation. So this is R, R0 e raised to minus kT, and this one. Then we have to draw the graph, right? Just like zero order, we have to draw a graph. That is also from which one? Equation 3. So equation 3, ln R equal to minus kT plus ln R0. And this equation is in the form of which one? Y equal to mx plus c. We know y equal to mx plus c means if we are drawing a graph between ln R and time, we will get a straight line like this. Okay, this in form of y equal to mx plus c means it is a straight line, and the slope of this straight line we will get the minus k value. Which value? Minus k value. Minus k means which is a velocity constant or rate constant, and this in a y-intercept we will get which value? ln R0. If they are asking draw the graph, means you have to draw ln concentration of R divided by time. It is a straight line. The slope of this line we will get minus k value, and the y-intercept we will get which one? ln R0. This is one graph. Okay. One more graph is there from which one? Equation 5. This is from which one? Equation 3. Okay. So from one more graph is there from which one? Equation 5. So both you have to learn, because they can ask the draw the graph, means you have to draw both. Or especially if they are asking draw the graph based on ln r equal to minus kt equation, means you have to draw this one. Okay. Then one more graph is there based on equation 5. This is our equation 5 now. So just rearranging that equation, log 10 concentration of R0 divided by R equal to what is that, kt divided by 2.303. K into, just here, kt divided by 2.303. K into t divided by 2.303. Just rearranging this equation. And there is a graph between log R0 divided by R, concentration of R, against time. Okay. And this is like this. Okay. And the slope of this graph, we will get which value gives k divided by 2.303. Slope equal to 1, k divided by 2.303. Okay. So this is a graph that is against log R0 divided by R gives a time, against time gives a straight line like this passing through the origin, and we will get the slope equal to which one, k divided by 2.303 is the slope value. Okay. So two types of graph is there. One is based on which one, equation 3. Equation 3 is very important because rearranging this equation 3 only we are getting different forms of the first order reaction. Okay. Then this is in the form of y equal to mx plus c. We will get this type of graph, and rearranging the equation 5 we will get a graph like this, and the slope equal to k divided by 2.303. Okay. So that is which one, the integrator rate equation. Then next is the example for first order reaction. 3 examples are given in your textbook. Any one or two you can learn. First one is which one? Decomposition of N2O5. What is N2O5? Nitrogen pentoxide. I am not writing the equation. It is there in the note. Decomposition of the nitrogen pentoxide. Then decomposition of nitrogen N2O. Okay. Then all the radioactive disintegration reactions are which one? First order reaction. Radioactive disintegration, alpha disintegration, beta nuclear fusion. Okay. So all radioactive reaction, disintegration reactions are also example for which one? First order kinetics or first order reaction. So decomposition of N2O5, decomposition of N2O, then all the disintegration, radioactive disintegration reactions are also example for which one? First order reaction. So clear all of you about the first order derivations and its examples. Next is we have to derive the expression for half-life for a first order reaction. Okay. Or show that the half-life, question may be like that, show that the half-life for a first order reaction is independent of the initial concentration. We know for a zero order reaction, the T half of the reaction was directly proportional to the initial concentration. What is T half? It is the time taken to reduce the concentration of the reactant to half. So here we have to prove that the T half of a first order reaction is independent of initial concentration, or derive the expression for T half for a first order reaction. Okay. So we know the integrator rate equation for first order, K equal to 2.303 divided by T log R0 divided by R. Our equation 5, that is the basic equation for first order. Okay. Then when T equal to T half we are going to find out. So when T equal to T half, the concentration of R will be equal to what? Definitely it will be the reactant. The concentration of the reactant will become half. Okay, so R equal to, concentration of R equal to R0 divided by 2. Then substitute these conditions in this equation. We will get K equal to 2.303 divided by, in place of T what we have to write? T half log concentration of R0 divided by R. R equal to R0 by 2. Okay. Then after that what you have to do? Just rearranging. T half equal to, I am taking the T half equal to 2.303 divided by K log this one and this one will cut, and this is 1 by 2, it will go to top, so we will get log 2. Okay. Then 2.303 divided by k into what is the value of log 2? 0.3010. We will get t half equal to 0.693 divided by k. So what is the value of t half? T half equal to 0.693 divided by k. Here any concentration terms are there or any initial concentration R0 is no. So T half is independent of which one? Initial concentration for a first half reaction. So T half equal to 0.693 divided by K for which one? A first order reaction. Okay. And in this case, for a definite fraction, the T half for a definite fraction will be constant. Okay. For example, I will show you T half. T half for the 100, it was 100 molar the concentration. It is converted to 50 molar. Okay. And here T half. Then 50 to 25 molar. Okay. Here also T half. That means this T half how much is? Suppose it is 5 minutes. This one will be also what? 5 minutes. It is not depending on the initial concentration. Okay. So the T half for a particular fraction or definite fraction is constant for which one? A first order reaction. How much? It was from 100 to 50. That much time will be for 50 to 25. Then 25 to 12.5. It will be a constant. Okay. Another thing is if T 20 percentage. Okay. So first it was 100 molar, it is converted, it's 20 percentage means what? 80 molar. Then it is again it is 60 percentage means what? It is 64 I think. It will be like this. And the time taken for this T 20 percentage, how much it is? Okay. So same time will be there here also. T 20 percentage. It was 2 seconds means it will be also which one? 2 seconds. Next will be also which one? 2 seconds. That is in case of which one? First order reaction. But in case of zero order reaction, it was directly proportional to which one? The initial concentration. Here for a definite fraction, what is that? The T half is constant. We will do the problems now. Okay. So clear all of you what is the T half for a first order reaction? T half equal to 0.693 divided by K. So it is independent of which one? Initial concentration. Clear all of you? Next is we have to do problems based on this first order and zero order. Zero order we finished now. First order now we finish. So 2 problems based on this. Okay. So first problem is in a zero order reaction, the time taken to reduce the concentration of reactant from 100% to 50%. Okay. From where to where? 100% to 50%. That is T half. Okay. Is 40 minutes. How much it is the T half? It is given 40 minutes. What is the time required to reduce the concentration from 25% to 12.5%? So it is given T half is how much it is? 100 to 50%. It is given 40 minutes. So we have to find out 25% to 12.5 to reduce the concentration from 25% to 12.5. How much is the time taken? Okay. We know for a zero order reaction, T half-life is directly proportional to the initial concentration. Okay, T half is directly proportional to the initial concentration. So here we know 100% to 50% it is given how much time? 40 minutes. Then so the initial concentration is depending upon the initial concentration. It is given 100%. 100% to 50% it is 40 minutes. Then 50 to 25 minutes we can write 20 minutes. How it is 20 minutes? Because the quantity is depending upon the initial concentration. Initial concentration is reduced to 50%. From 50% to 25%, only the half of this 40 minutes it will come. That is 20 minutes. Then 25% to 12.5 minutes percentage, how much it will be? The half of 20 minutes, that is 10 minutes. Okay, because the independent, it is directly proportional to initial concentration. That means the initial concentration is reduced. According to that, what will be also reduced? The time taken to reduce the concentration. So it was 100 to 50, 40 minutes. Then 50 to 25%, it is again half of this, that is 20. Then 25 to 12.5 minutes, it is percentage, it is 10 minutes. Okay, clear? Yeah, that is in which one? Zero order. Same type of problem in first order. In a first order reaction, time taken to reduce the concentration from same 100 to 50 percentage is 40 minutes. Same only. What is the time required to reduce from 25 percentage to 12.5? Same question, but one is zero order and the other one is which one? First order. Zero order means what? Depending upon reducing the initial concentration, the time taken to reduce the concentration will be also decreases. Right. And then here means we know the T half is independent of initial concentration, and I told you for a definite fraction or percentage it is taken as a constant. Okay. So here 100 percentage to 50 percentage it is given 40 minutes. Then the question is 25 to 12.5 percentage also will be which one? 40%, 40 minutes, because it is given, it is independent of initial concentration. Initial concentration, how much, it is also not a problem. Okay, it is not depending upon the initial concentration. Okay, and how much, it is constant. For a definite fraction it is constant. Here it is, what is that? 50 to 100 to 50 it is 40. So it is 25 to 12.5 percentage also it is which one? 40 minutes. Okay, clear? Okay, so this is the comparison of these two problems. This is exactly, it is the time is also reducing. Here the time will be constant in case of which one? First order reaction. So clear all of you, that is about today's topic. Okay.